This is Mrs. O'Neill for AP Chemistry, Chapter 7, Section 2, Effective Nuclear Charge. Your objective is to explore the many properties of atoms that depend on the net attraction of the outer electrons to the nucleus and the average distance of those electrons from the nucleus. So we need to know that the net positive charge of that nucleus is experienced by the outer electrons, and it is called the effective nuclear charge. So again, pause the video, fill in the blanks, read as you write, and then play to hear my words. So the properties of an atom really depends on the electron configuration, which we already did. And that tells us where those electrons are, and it helps us understand how the bonding occurs between atoms. Do they transfer their electrons? Do they gain or lose those electrons? Do they share those electrons? Do they make multiple bonds? All of those things. But then it also depends on the attraction between those electrons and the nucleus. Well, how hard or how strong that attraction is between that nucleus and the electrons are also going to depend on what's going on and how they interact with other atoms. So Coulomb's law is really important, and if we haven't done so already, we will be doing a POGIL, P-O-G-I-L, on Coulomb's law, because they do bring this up in the AP exam quite often. What's that concept of Coulomb's law, what it means, and what the trends are on the periodic table. So Coulomb's law, again, if we haven't discussed it already, is how strong that attraction is between those two charges, and it's going to depend on the magnitude of the charges and the distance. So Coulomb's law really takes two things into consideration: the charge, positive, negative, how strong that attraction is, what the magnitude is it +1, +2, +3, and the distance between them. So that attractive force between that electron and nucleus also depends on many things. Again, the magnitude of that nuclear charge, again, that distance. The force increases as the nuclear charge increases, and of course it's going to decrease as that electron moves farther away from the nucleus. So the farther away that electron is from that nucleus, of course, there's going to be less force of attraction. So there's all these things that are going to kind of come together and say, okay, which element or which atom or which compound is going to have a stronger force of attraction than something else. So we can do a little bit of comparison. So this Z effect, or the effective nuclear charge, is really the ZEFF. It's the effect on the electrons on the nucleus, okay? So it's the force of attraction between the electrons in the electron cloud and the positive nucleus, right? Because that's where those positive protons are. So it's that force of attraction between the two. So we're going to treat each electron as if it were affected by the net charge of the attraction of the nucleus and the repulsion of the electron. Okay, so we're gonna look at each individual electron and what's going on. So is smaller, the Z effect is going to be smaller than the actual nuclear charge Z. Okay, so this Z effect is smaller than the actual nuclear charge number. Okay, so that's kind of weird to kind of think about. So we get this nuclear charge because, again, chemists really like to put value, right? They like to quantify everything just so you can have the better comparison. They just don't want to say one's smaller than the other or one's bigger than the other. Well, how do you know that? Well, the reason you know that is because they like to quantify everything. So this way we can say, well, the nuclear charge is this, however, this Z effect, this force of attraction, is really going to be smaller than that. So where do we get these numbers? Well, this Z effect is really Z minus S, or Z equals the atomic number, and S is really going to be those shielding electrons. Well, where do we get those shielding electrons? Well, think about the atomic number is your total number of electrons, right? That hopefully makes sense. Now, these shielding electrons really come from those core electrons. The core electrons are going to shield the nucleus from getting to those outermost, aka valence electrons. So this Z effect is different. Okay, this nuclear charge is different because we're quantifying it. So let's look at sodium, for example. And this is where you might want to kind of listen to everything I have to say for sodium, and then right before we get to our next slide or example, I believe it's of sulfur, then you might either want to pause and then fill in the blanks, or you might want to then rewind and hear it again. So if we look at sodium, sodium normally has 11 protons, so that would be a plus 11 in the nucleus, and it has 11 electrons. So, but what happens is if we take those 11 electrons, now we got to think about this. Really, it has 10 core electrons and 1 valence electrons. So we kind of have to separate those electrons into both. How do we know that? Well, sodium is in group 1, and everybody in group 1 has 1 valence electron. So if I take the total number of electrons, which is 11, minus the 1 valence electrons, then I have 10 left over inside as core electrons. So the Z effect really would be 1. How did we get that? Well, the Z effect, again, is going to be 11, which is the total number of electrons minus those core electrons, and we get a plus 1. Now, notice it's very similar to its charge, but it is not the charge. It's not the oxidation number of sodium. This is what we call the Z effect. And I'm saying that specifically because when we look at sulfur, which is our next example, it's going to be quite different than the charge number. So right now I pause, maybe make sure you're understanding this information and fill in your notes. So now let's look at the Z effect for sulfur. Again, you might want to just play everything I say and then fill in your notes. So let's start with our atom of sulfur. 16 protons inside, 16 electrons. But now let's take those electrons and separate them into core and valence. So do you know what group number sulfur is in? 16. Do you know then how many valence electrons that would be? 6. So can you do 10 minus 6? I should say, yes, I'm sorry, 16 minus 6 to get the 10 core electrons on the inside. So hopefully that makes sense. Now let's look at the Z effect. The Z effect is really plus 6. How do we get that? Well, 16 minus 6 equals plus 6. So again, this is really its valence electrons. It's not really its charge. But plus 6 is greater than plus 1. So the Z effect, or the nuclear effective charge on sulfur, would be greater than of sodium. Again, chemists like to quantify everything. So obviously plus 6 is greater than plus 1. What does that mean in the Coulomb slosh, nuclear charge, effective nuclear charge, Z effect, all of that, all of those terminology kind of mean the same thing. It means that sulfur's attraction between the nucleus and the electrons is going to be stronger than the attraction of sodium's nucleus and electrons. So what then is the trend of the nuclear charge? Well, obviously every time we're increasing the number of protons, we're increasing the number of electrons, we should be increasing the effective nuclear charge. So as we go across a period, it increases, and as we go down the group, it increases. This is very different than what you're used to, because you're always used to the trends going in the opposite directions when we're talking about across a period and down a group. However, in this case, they both increase. Just one is going to slightly increase and the other one's going to really increase. So again, if you have more protons, you're going to have a greater nuclear charge. So again, it's kind of like reading a book, right? You're increasing across and down like reading a book. So pause the video, see if you can read this information. Again, I don't ask you reading too much, but please read this, pause it, and then see if you understand the trends here and what's going on. Hopefully you paused, read things over. Hopefully that makes a little bit of sense as to what the trends are. Here again is another picture of the trends. Again, we have the effective nuclear charge, which would be the Z effect, and what's happening again between here's period 1, here's period 2, and here's period 3, and of course, and it's related to its atomic number. So pause and again look that over, because they do like you analyzing graphs. So again, here's the trend. Effective nuclear charge just basically increases across and down. So we have the smallest nuclear charge here and the greatest nuclear charge here. Again, pause the video, make sure you're understanding what's going on, understanding the core versus valence, and again, that nuclear charge is going to be based off of those core electrons, the shielding. So what is this shielding effect I've been talking about? Well, the valence electrons are shielded from the pull or the charge of the nucleus by all of those other core electrons. So the shielding, the nuclear attraction on those electrons. So again, you have a positive inside here, and you have this negative all the way on the outside, those valence electrons. But you have all of this other negativity in the middle, and these core electrons are shielding the attraction between those valence and the nucleus. That should kind of make sense, but let's put it into a little different perspective. So if I'm teaching here in the front of the class, and here's all of our students, so here's all of those core electrons, and here's the one student all the way on the outside, and there's a door right there. Which one, the valence electrons or the core electrons, can leave the room easier? Well, of course, the teacher is going to have a hard enough time telling that teacher or grabbing that student, to stay inside the classroom if he wants to run out, because the teacher is going to be shielded by all these other electrons, right? These electrons are going to say, no, Mrs. O'Neill, you got to stay back here as X, Y, and Z leaves the room. Okay, so that's what shielding means. So the core electrons are the shielding electrons from the nucleus to those valence electrons. Oh, yeah, and I circled it, obviously the red one. So again, what's the difference? The core are doing the shielding, and the valence are experiencing the shielding effect. So again, here's our trend. Make sure we're understanding that more core electrons are shielding. You have a greater nuclear effective charge. So again, pause, make sure to read this and understand the attraction and the repulsion between the nucleus and the electrons and other electrons. Again, I don't ask you to read much, but read this over, very important. And I will see you in class.